In this video, I will walk you through how to interpret Proton NMR Spectra questions. Before we start today's question, I'm going to go through 3 basic rules you need to follow every single time when answering NMR questions. Rule number 1 is the number of peaks in the spectra, so the number of distinct peaks you see in the spectra, is equal to the number of unique hydrogen environments. Number 2, the area under the peak is equal to the number of hydrogens in that environment. And then number 3 is, so the greater the electronegativity of the hydrogen environment, the greater the chemical shift. So these are the rules that I work by. We're going to apply these to the spectra on the right and identify what the molecule is. I will be using the datasheet I have attached in the description below this video, so please check that out. But if you have your own data table from school or college, please use that. So the structural isomers with molecular formula C4H8O2 are carboxylic acids or esters. So there's a big clue there. So let's go ahead and apply these rules. So the number of peaks, how many peaks can we see? There are 3 distinct peaks. So therefore this molecule must have 3 hydrogen environments. And now we need to look a little bit more in depth at where these peaks are situated. If we look at the peak at approximately, so this one, that's at about 4.1, 4.2. And that's always a giveaway with organic molecules, something at 4.1, 4.2, because it's usually the same thing. And that is a hydrogen bonded to a carbon, which is directly attached to an oxygen. So there's a big clue there. But we know it's a carboxylic acid or an ester. So what does the carboxylic acid functional group look like? It's C double bond O, OH, and then the ester is C double bond O with just an oxygen, and then usually either side a carbon. So if we look at the spectra, the datasheet, we can see that the carboxylic acid proton, which is this one, has a chemical shift of around about 11 to 12. Well, if you look up here, there's nothing there, is it? So therefore, it cannot be a carboxylic acid. It is an ester. Okay, the next thing we need to look at is the other environments. So if we look at that one, in the datasheet, you've got 3 options there. You've got a benzene ring. Well, there's no benzene ring, so it's not that. There's a CN bond that is in that range. Well, it's definitely not that because there's no nitrogen in the molecule. And then there's the C double bond O. So therefore, that one must be the C double bond O. And there's another giveaway. So now is the appropriate point to bring in what are called splitting patterns. So we can see that this is a singlet, this is a triplet split into 3, and this is a quartet split into 4. Just zoom in so you can see that. So you can see there's 4 peaks there, 4 splits. Let's just quickly go over splitting patterns. So splitting patterns are determined by what is called the N+1 rule. So N is equal to the number hydrogens in the adjacent environment. So if you have 2 carbons next to each other, both with hydrogens on them, what you have to do is you look at the carbon immediately next door to the environment you were considering, and then you count the number of hydrogens. So for example, so there's 1 hydrogen environment, and there's a second hydrogen environment. Let's just say we were looking at this one, right? We look at, to work out the splitting for this one, we look at the carbon immediately next door, which is going to be this one, and we look at the number of hydrogens on it, and we can see there's 1, 2, 3. So N equals 3 for that environment. So therefore the split will be 3 plus 1 makes 4. So this particular one would be a quartet. Then for this one, N would be, so we'd look at the carbon next door, which is that one there, would be 2. So 2 plus 1 equals 3, and that would be a triplet. So this particular molecule I've just made up, which is chloroethane, would have a triplet and a quartet present in the spectra. If the split, well, when I say split, if the peak is unsplit and there are no neighboring environments, so for example, which is the situation here, where we have a carbon maybe with hydrogens like that, the carbon next door is a C double bond O, or is bonded to something else, so maybe there's a fluorine there, so it has no hydrogens, then for that, N would be 0. And then 0 plus 1 makes 1. So this environment would remain as a singlet, which means unsplit. So that's exactly what we have here. So we can see at 2, a carbon directly bonded to a C double bond O. It is completely unsplit, which means this must be a CH3, because the CH3 bonded directly to a C double bond O doesn't have any neighboring hydrogens. So therefore 0 plus 1 would be 1, and that would be a singlet. Now we can just go back to the drawing. We know that there's a CH3 directly attached to a CO and a single bond O, which is the ester bond. So now that only leaves us with these last two peaks, which is the quartet and the triplet. So a quartet is going to be formed when the hydrogen environment is annexed to a carbon with 3 hydrogens, because 3 plus 1 would make 4, which is a quartet. And then a triplet would be caused by being next to a carbon which has 2 hydrogens, because 2 plus 1 makes 3, a triplet. So therefore this carbon there, which is that one there, must be a CH2, which is bonded to a CH3. Because if I just circle that, the immediate environment is a carbon with 3 hydrogens, so 3 plus 1 is 4. So that would make that a quartet, which is that there. And then the CH3 next to the CH2 would be a triplet, which would be that one there. And also this, the location of that peak is around about 1.3, 1.4 if you look at it. And that fits perfectly with the data sheet, which says between 0.8 to 2, you have this C bonded to the rest of the molecule, rest of a carbon chain and a hydrogen. So that bit there is basically that bit there. So it's perfect. So ethyl ethanoate would be the name of this ester. Okay, right. This is just a warm-up today. This is just one of many videos I'm producing on proton and carbon NMR. So check out the link below and go and watch the next one, because they get progressively more difficult and require longer, more thorough explanation. But I promise you, this is what I'll be using every single time.